one of these. And we'll get started. So there's a few announcements that are out. One is that I'm not going to be able to give a live lecture Thursday morning. So sleep in if you want. I will have a prepared lecture up on the website for Thursday lectures material. Well, I'm hoping I'll have it up later today, but could be late Wednesday night before I actually get it done. Anyway, it will be there for Thursday morning. So don't look for me live, but look on the Canvas course page for the video and the accompanying notes. Also, there's an announcement about the midterm next Wednesday. It'll be the next Wednesday, the 24 hours of Wednesday. We'll have the same format as the assignments, 4 Part A questions, 1 Part B question to be submitted separately in PDF format to the Canvas page. You know, just because of the way these things work, it'll be 1 minute after midnight, it will be open. And 1 minute before midnight on Wednesday, it will be due. Before I go on, any questions on those two things? Okay, let me share the screen. And let Brian take over with the notes. We're going to talk about some generalizations to the boundary value models that we've been considering, boundary values in 1D and the corresponding heat equation. So generalizations to the equations and the boundary conditions that lead to new kinds of eigenvalue problems. We're still going to be in the game of looking for series solutions. And this leads us to something called Sturm-Liouville theory. There's some of which we've seen about the orthogonality of some of these boundary value eigenfunctions. And others, it's a little bit more deeper in theory, and I'll just tell you the theory and possibly ask a question or two on the next assignment to prove some of that. But the most difficult thing is a completeness result, which of course I'll describe to you, but that's not Math 400 material. That's an analysis course material. Okay, so let's look at a generalized. Let's look at a. Oh yeah, let me exit full screen so that my Slack channel is open and I can see if questions come from the audience. I'm going to look at a generalized boundary value problem. Or let me look at a generalized heat equation first, and then we'll see how it goes into a generalized eigenvalue problem. Okay, so remember we did the derivation where I had a heat content term, okay, I'm blanking on the exact name, times the density. The product of these things gave the volumetric heat content. And then I'm also going to have a thin rod which has varying cross-section. Okay, that rod doesn't look particularly thin, but use your imagination. And if you look in detail of how varying material coefficients will affect the heat conduction, remember there's the heat, there's the conductivity, thermal conductivity. There will be an area term in here. And it will look like this. And you might wonder, well, why am I keeping this term like this instead of expanding it out, right? With the product rule. And it's because if I leave it this way, I'm going to end up with a symmetric eigenvalue problem, which is what I want. So if the physics tells me to do this and the mathematics is better if I leave it like this, then okay, I'm going to leave it like this. Now, just to be fair, or to be clear, there are other types of problems with varying coefficients which lead to different forms of this kind of problem. And so this is where the modeling that we did at the beginning is useful. We can go back to that, look at it, and understand how the variable coefficient problems should work. Okay, so when so when C, rho, K, and A were independent of X, we had the scaled problem. Right, this is the, I'll say, the vanilla heat equation. Nothing wrong with vanilla, right? We got a lot of insight from that work. Okay, so if I start from this though, right, I'd want to write it as okay, and same as before, right? I could find series solutions to this problem, right? If I looked at linear operators, so if I looked at eigenanalysis of linear operators of the form, I'm going to have L of phi is 1 over A of X. So that's all of this stuff. Times B of X phi prime prime. That's all of this stuff. Right, so I'm going to look for eigen analysis of that. Will give series solutions to this generalized heat equation. Oh, but remember, if I'm going to talk about linear operators, boundary value operators, if I'm going to do the eigenanalysis, I have to tell you what the boundary conditions are. So let's generalize the boundary conditions a little bit too. So if you think back to the derivation of the heat equation in the thin rod, right? I had minus ux. This term is proportional to the heat flux in the plus X direction, right? Okay, and that's why it comes up in this term up here, right? The constant of proportionality is this K, right? This thermal conductivity, and heat flux is energy transport per unit cross-sectional area. So that's where the A comes in. So this term in the green box is the heat flux, and the change in the heat flux at an X coordinate is what is heating up this rod locally in this problem with no external heating. There's no F term here in this heat equation I'm looking at. But remember, we've got this Duhamel's principle, which says basically if we understand the initial value problem for time-dependent problems, we can handle the forcing term as an integral. Okay. So if I know that this is proportional to the heat flux in the plus X direction, then if I have boundary conditions, U X at 0, okay, I've got time in here, so I'll put X equals 0. If I set this to 0, this is insulated condition. Right, so it's an insulated condition, which we could call based on this particular application. But in mathematical terms, this condition with a derivative is called a Neumann condition. And that it's equal to 0 over here. Let me get a different color. This then together, this is a homogeneous Neumann condition. And remember, if we've got boundary data that's not 0, that's a separate problem, right? We're allowed to break the problem up into pieces and just look at the problem with homogeneous boundary conditions here. And later on, after we've talked a little bit about some transform methods, we'll come back to the forcing terms at the boundary. Okay, so let's backtrack and say if I had a boundary condition, BC for boundary condition of U equals 0, giving values of the function on the boundary, right? In our application, that's specifying the boundary temperature. Mathematically, this is called a Dirichlet condition. Dirichlet and Neumann, famous mathematicians. And when it's equal to 0, then it's a homogeneous Dirichlet condition. Okay, and let's be clear. You can't apply both. This is a choice. You can't say the boundary is insulated and it's 0 temperature, right? Because if it's insulated, then it's going to be whatever temperature is found from the dynamics inside the rod, right? So now, of course, there's a third one. Okay, and it's, oh, can I get the sign right? Yeah, okay, so now I'm going to look at X equals 0 boundary condition. So there's the third alternative. Okay, and there's only 3 alternatives in this linear setting, okay? And that's a mix of the two, right? I'm going to have alpha bigger than 0 is going to be a given constant. And I'm going to say that u minus alpha u x is 0 at x equals 0. Or I could write that alpha ux is u. Right, remember alpha, if alpha is positive, right, alpha ux is proportional to heat flux in the plus x direction. Do I have the sign wrong? No, alpha ux without the minus sign is heat flux in the negative x direction. So if ux were positive, this is heat flux out of the left end. And this says that the heat flux out of the left end is proportional to the temperature. So this is like a Newton's law of cooling kind of term, where you have the left-hand end is in ambient temperature of 0, and the hotter the temperature of that end is, bigger than 0, the more heat is conducted outside of the rod. So this is like a Newton law of cooling kind of term. And in the math lingo, there's another mathematician, less famous. This is called a Raman condition. Okay, and just like before, when you set it equal to 0, that is a homogeneous Raman condition. I won't write that down. Okay, and then if I were going to have at the right end, I'd have to have u plus alpha ux is equal to 0 to get the physics and the mathematics right. Okay, so now I want to go back to let me write it out again, right? Now I want to look at a linear operator. Now I'm going to add the boundary conditions. Right? It's 1 over a of x, b of x u prime prime, right? And now I'm going to give boundary conditions. C1 phi of 0 plus C2 phi prime of 0 is 0. Right, and these are going to be given constants. Not both 0. If they're both 0, it doesn't tell me anything. But this then includes all of the boundary conditions we've had before. I could take C1 equals 0 and C2 equals 0, and I get a Dirichlet condition. I could take C1 is equal to 0, C2 is equal to 1, and I get a Neumann condition. And I could take C1 is equal to 1 and C2 is equal to alpha, and I get the Raman condition. And I'm going to have some kind of conditions at the other end as well. And here I'm going to have D1, D2 also not both 0. Okay, and this thing in here, right, this is a Sturm. Oh, I'm going to want to look at the eigenvalues of that. And I've got u instead of phi. Okay, let me fix that up. I'll give you a minute to fix that in your notes. Okay. And if I worked out the eigenvalues and eigenfunctions of this, I would get a way to find series solutions for L of U is F, and UT is L of U with U at time 0 given. And UT is LU plus F with U equals 0. And this last one here, this is by Duhamel's principle. Okay, so that seems like it's a useful thing to do. So let's talk about that problem. And I can write out the properties of this thing, and motivated by the physical application that we had, right? So here's the theory, and the theory
Brian?
is, yeah.
Sorry to interrupt. You've got a question in the chat.
Oh, yeah. Yeah, we're not considering the time derivative at all here, just like when we did the sine series for the heat equation. All we needed was the series solution to this. And I'll do some other examples where we'll put it together to remind you of how that goes. So let's concentrate on this problem for now, and then you'll see a second time how we get the time-dependent problem out of it, if that's okay. Okay, thanks, Maricela, for yeah, letting me know. I got all interested in Sturm-Liouville theory, or Sturm-Liouville theory. So this theory, and we're going to be motivated by the physics application, which kind of matches the math. So this assumes that A of X and B of X are non-negative. Okay. And you can extend some of this theory to where there are isolated points where one of these things is 0, and it gets tricky. In fact, one of the things that we'll look at in the next lecture will have that. And I'll just say, with a lot of work, this theory carries over to that problem as well. So here, I'm going to summarize the theory as follows. There's a bunch of points. So we've looked at some of these things before in simpler cases and saw symmetric problems led to real eigenvalues. And just from the way we've written this out in this form, I'll say it's the same story. All of the eigenvalues are real. And also they're all real and negative. All the eigenvalues are simple. What does that mean? There is only one eigenfunction for each eigenvalue. And remember the example to keep in your head, it's the sine series, right? A is identically 1, B is identically 1, right? That's U double prime is lambda times U with homogeneous Dirichlet boundary conditions. We get lambda is minus n squared pi squared, and each one of those things just has a single eigenfunction. It's sine n pi x. Now, when I say there's only one eigenfunction, remember, if you've got an eigenfunction, you can multiply it by any non-zero number you want, right? And it's still an eigenfunction. So what I'm really saying is there's only one, the eigenspace has dimension 1, is what I'm saying, right? Okay. Okay. There's the orthogonality, which is going to come out in the way that we looked at with the symmetrization thing. If I write this thing out as b of x phi prime prime, this is lambda a of x times phi, right? And exactly the same way that we expect, these guys are going to be orthogonal with weight a. So if phi n of x and phi m of x are two eigenfunctions, corresponding to different eigenvalues. So I got the sine n pi x and the sine m pi x. How do we know? Because the theory, I'm just quoting the theory, okay? These are things, in fact, you could prove with techniques that you saw at the beginning of the term, along with this next one. But I'm just telling you Sturm-Liouville theory, Sturm-Liouville theory. Okay, and then I have orthogonality in this following way. The sine series were orthogonal with just this usual inner product. And you've seen how these guys are going to be orthogonal in this weighted inner product. Right, so here I've scaled my problem to the unit interval. Okay, yeah, I've got the unit interval. Okay, so this is this is a kind of orthogonality I've got in the notes. But these are notes from previous time I taught the class, and we've talked a lot more about this, so you know where that's coming from. Okay, here's some other things from the theory. The eigenvalues form an infinite series. So there's an infinite number of them. And lambda n goes to minus infinity as n goes to infinity. So I can order them in this nice way, okay? And remember, we actually care about this order. Remember, in the time-dependent problem, these eigenfunctions lead to time-dependent behavior that looks like e to the lambda t, lambda j of times t. And so These guys in that case are all decaying exponentially faster and faster. This is just like the sine series where you had sine n pi x multiplied by e to the minus n squared pi squared t. Those terms don't last very long in time. It's the same story in this generalized case with the generalized boundary conditions and the generalized terms in the equation. Okay, and even in the, it's not exponential, but even in the boundary value problem, remember you're dividing by lambda j in the solution process. So these bigger ones are going to get damped more quickly. Okay, now here's the hardest one to show. These are all kind of these are all kind of accessible with the Math 400 techniques. This one is not. Let's suppose f is continuously differentiable. Okay, and you can weaken this condition, okay, in the theory in most cases. Then if I take this sum, so this is going to be the analog of the sine series with Fn. Well, okay, what am I going to do, right? I'm going to say I want this to be f of x, this sum, right? Right. So what would you do, right? You would say, well, if I want this to be this function, then I would multiply by a of x, right? I would multiply by phi m of x, and I would integrate, and I would just get one term, and that term would have value right? That would be like if a was 1, right? This would be like the sine series coefficients, except that these guys aren't normalized, so you have to have a normalizing term, which is just this positive constant. This was the half for the sine series, and it's whatever it is for these generalized eigenfunctions. Okay, well, okay. So then this, with that, converges. This thing here converges pointwise to f of x. Okay, so let's just think about this, right? This is basically saying that the set of all of these eigen functions is a, I'll say, a basis for a basis of functions in a certain space, which I'll leave a little bit vague. Unless you've taken math 320 and 321, in which case I'll say it's L2. It's a basis of L2. Now, why is this a tricky result? Let's think about the linear algebra setting, right? The linear algebra setting is I've got a symmetric matrix, right? And maybe it's symmetric in a weighted inner product, like we've seen before, right? Here is the weighted inner product in this case. But okay, let's just talk about a regular symmetric matrix. So you know it has real eigenvalues, and it's got n linearly independent eigenvectors. And in the finite dimensional case, right, once you've got n linearly independent vectors, then you know you've got all the directions that there are, right? That means you can write any vector as a linear combination of those vectors, and you're done. In this infinite dimensional setting, it's not so clear. Yes, I have an infinite number of eigen functions, but how do I know that there's not some directions left out, right? Because I can have an infinite number. I could take one of the functions out. I'd still have an infinite number, but then suddenly there would be a bunch of functions that I can't represent with what I've got left. So this is a deep result from analysis that, in fact, once you have found all of these functions, you can really use them to solve any problem. Okay. So we've proved sort of variants of some of these things at the beginning in previous notes. It's written out in the posted notes from the last lecture, which we were just slow getting through, so we haven't done that yet. These later ones, these are really interesting mathematical questions. There's some other things that come from Sturm Liouville theory about the interlacing of roots of the functions that come out of these things. But let's leave that as given. Well, it's probably good to have an example at this stage. So let's do an example. Okay, so it's going to look like all I'm doing is the sine series, because I'm going to just have the second derivative. And I'm going to have a simple boundary condition on the left. So I'm just going to have a homogeneous Dirichlet condition on the left. And if I had a homogeneous Dirichlet condition on the right-hand side, then I would just get the sine series, right? Except so now I'm going to put something like this. I'm going to have a different boundary condition. That makes the algebra working out this problem a little bit easier, because the interior equation is simple and all the complexity is now in this boundary condition. Okay, so if I look at phi double prime is lambda phi, so the theory or a direct check gives lambda has to be less than 0. So I'll call it minus mu squared. Right, so that would tell me that phi has to be a sine mu x plus b cosine mu x. Right, and because I've got phi of 0 equals 0, that tells me that b has to be 0. So I can put a big cross on that guy. Right, and if I had the same boundary condition I had before, I'd just get u was n pi, and I'd get the sine series. Now I'm going to get something a little bit different, right? So I need a naught to be 0 to get an eigenfunction. So I've got to have phi at 1 plus alpha phi prime at 1. This would have to be a times sine mu plus alpha cosine mu. This would have to be 0. And since A can't be 0, this would have to be 0. So this is my eigen value criteria. Oh. I think I've got a mu missing. Is that right? Okay, that would be good because that's what's in my notes. And if it wasn't right, then I'd have to really think on my feet. Well, okay, I'm sitting down, but you know what I mean. I'm terrible at thinking on my feet. I was just there was something recently where it was at a departmental meeting, and someone said, "Gee, if you're trying to think, talk, and write at the same time, okay, you got to be really good, or else you're in trouble." Okay, so let me write and talk, but not think. Okay, so good. Thanks for thinking for me. I get mu equals 0 is a root of that. Yeah, but that leads to lambda equals 0, and it turns out that you don't get an eigenvalue that way. So otherwise, I'm looking for the intersection of tangent of mu with minus alpha mu. You know, if you have an alpha and you want actual numbers, then after this picture, you could go to Wolfram Alpha and you know, look them up. But if you're interested in the sort of range that they're going to be in, here's a picture and gives some qualitative information. Tangent goes bad at pi over 2, 3 pi over 2, and 5 pi over 2. And it is 0 at multiples of pi. And here we go. Here we go. Goes asymptotes like this. And I'm looking for the intersection. I'll get a different color. So here's tangent. And I'm looking for, here is minus alpha mu. This is the mu axis, and I'm looking for these intersections. Here was this trivial one, right, which didn't lead anywhere. Here is the mu1. And remember, right, in your head, you know that this is the most interesting one, right? It's the one that leads to the slowest decay rate when we look at the heat equation version of this. It's the least damped mode in the boundary value problem. So that's the one we're interested. Remember though, the eigenvalue is not mu1, it's minus mu1 squared. So don't forget that part. And then of course you can see how you get the infinite sequence of negative but increasing in magnitude eigenvalues from this picture, right? So, okay, it's an example of the theory without a proof of the theory. So I'm going to get eigenvalues, lambda n minus mu n squared. And again, there's no analytic formula for these things. So exact values. I think when these notes were written that I'm going off of, I don't think Wolfram Alpha was a thing. So it says, you know, use Newton's method or F0 in MATLAB, but now I would say, so no exact formula. Use Wolfram alpha. Or the symbolic tool of your choice. Okay, and also, now I don't have an A term here, right? Right. So also I know. Whoop, what happened? Also, I'll say from the theory, I know that the integral from 0 to 1 sine mu nx sine mu mx dx is 0 if n is not equal to m. And I also know that if I look at this sum, that this will converge to f of x when I pick my coefficients equal to the following. And this is the normalizing factor down here. That's the 1/2 from the regular sine series. And now it's going to be whatever horrible number that turns out to be in this particular case. So, of course, I've got a series that I'm going to use to solve the boundary value problem and the heat equation problem when I've got those different boundary conditions. It's a series that's got signs in it, but it's not the sine series, right? When we talk about the sine series, we mean that particular one that came from the homogeneous Dirichlet conditions. This one is a series that's different, right? Mu n is not equal to n pi. It's equal to some other stuff, right? So I gave it a name. It's probably got a name somewhere, but I'm going to call this the sine alpha series. You give me an alpha, any alpha, I've got a different sine series that's tailored exactly for this problem. Okay, so well, let's use this to solve some problems. Okay, well, I can solve 3 problems, right? I can solve u double prime is equal to f of x. I can just solve this boundary value problem. And I can solve it with these u of 1 plus, minus, what was it? Plus. Did I really want plus? Or did I want minus? Okay, let me just make sure I got the sign right at that. Oh yeah, okay, yeah. Plus sign is the right sign. There's one that's a positive feedback, which of course we don't want. Okay, how am I doing for time? Okay, yeah, I'm good. So if I wanted to solve this problem, I would have these coefficients, right? And I would get u would be a sum. I'd have these sine mu and x's, right? And all I would take is the Fn and divide by minus mu n squared, right? Right, how do I know that? Because when I take the second derivative of u, I get the second derivative of the sines, which satisfy the boundary conditions, right? And I get that they have a multiple, an eigen value of lambda n, which was minus mu n squared. So this form satisfies the equation. This is just like the sine series where I divide by minus n squared pi squared, except now the numbers are all different because the problem is different, right? Even though the interior part's the same, the problem is different because the boundary conditions are different, okay? What about if I had ut is uxx with u at x and 0? Okay, I'm going to use f of x here just because then I can use the same thing. Then I get u of x and t is a sum of n equals 1 to infinity. I'm going to have fn, and I'm going to have e to the minus mu n squared t. So once I've got this sine series, sine alpha series, right now suddenly I can solve all kinds of problems where this this thing shows up. Oh, and I should say that for this problem, I've got the u at 0t is 0, and u1 of t plus alpha u x at 1 of t is 0. Okay, and I'll leave this one. You can also get a series with Duhamel's principle. Maybe that's a good assignment question for the next assignment. There's no new assignment coming out this week because of the midterm next week. So I'll save it. I'll save it for the future. In the notes, there is a variant of the heat conduction problem with the varying materials. Here, there's more variation because the terms in the orthogonality weight are also discontinuous. I'll let you look at that one because you worked on something that was quite similar. And the next one I want to go to. So example 2 of Sturm Liouville or Sturm Liouville. I'm going to do an example with a small parameter. And so there's going to be some linearization going on. This is an important tool in applied math. And this is a course that says applied in the title. So I want to go with that. You've seen some examples with the epsilon already. There was the linearization of the stretched wire, weighted stretch wire, which led to the linear problem that we started with studying. I guess I want to do a little bit of warm up here. You've seen it, and if the linearization that we've looked at so far all makes perfect sense, then this is warm up that you don't need. So I'm going to do two easier examples first. Okay, so I'm going to look at a really simple one. It's finding the roots of a quadratic equation. Okay. So when I write it like this, then you already know that the roots of that quadratic equation are 1 and 2, right? But let me write it out so that it started off like this. And the roots are x equals 1 and 2. Okay, so this is a warm up. This is a toy example to show you a concept, not an example where you would actually need to use this technique. So what about if I change the problem slightly? So in your head, think of x equal 1, that solution. That was the unweighted wire stretched across. Okay, so it was just straight across, right? That solution is easy to find. This solution is easy to find as well, right? Because we started off knowing what it was. So what about if instead of this equation, I'm trying to solve this equation, where I change the 2 to 2 plus epsilon, right? This is like, instead of the stretched wire with no weight on it, I've got the stretched wire with a little bit of weight on it, okay? Well, of course, it's a nonlinear problem to find x, but if epsilon is small, we could look at a related linear problem, because of course I'm thinking here of epsilon as being small. Of course, how small does it have to be for this to work? Well, that's an interesting question, okay? Well, certainly this thing should have a root. Near x equal 1. The stretched wire we looked at, if the weight was small, should and did have a solution that was near the wire stretched straight across. So it's the same story here. I should have a root near x equal 1 if epsilon is small. In fact, I should be able to find a whole parameter of solutions, x depending on epsilon, with x of 0 equals 1. So when I don't have x, when I don't have any epsilon, I'm interested in this solution 1. And I could do linear approximation. I just have 1, and I've got a linear perturbation, and all I need is the derivative, right? That's tangent line approximation. And this thing, well, I don't have x as a function of epsilon in front of me, but I can do implicit differentiation. Of the thing in the red box. So if I've got x as the function of epsilon, then if I take the derivative and I use the chain rule, I get 2x dx by d epsilon. And then I've got minus 3 dx by d epsilon. The 2 doesn't depend on epsilon. The epsilon, when I take its derivative with epsilon, gives me the 1. Right, so that tells me dx by d epsilon is minus 1 over 2x minus 3. I want to evaluate that at epsilon is equal to 0. Well, there's no epsilon here, but I need to know what x is when epsilon is equal to 0. But I already said I knew. I'm linearizing around a known solution. That's the x is equal to 1. So let's evaluate at x equals 0, where x at 0 is 1. And I get that dx d epsilon is 1. So the root is x is approximately equal to 1 plus epsilon. So that's how you would approximate the roots. And if you wanted higher order corrections, you could work out x of epsilon. Well, I've got this term, which is the first term in a Taylor series approximation. I could add another term. And I could work out these derivatives by repeated implicit differentiation. Back to Math 100. But one of the more complicated things from Math 400, I'll say. Okay, so that's a good way to conceptually think about it. I'm just going to show you an alternate derivation. That's closer to what people actually do in applied math. And that is I'm looking at this thing. I'm going to say, I know that x of epsilon has the form 1 plus beta epsilon. With beta, I'm not quite sure what that is yet, right? Well, it's the dx by d epsilon at 0. And I just take this and I plug it in. So what do I get? I get 1 plus beta epsilon. Oh, this is an approximation, sorry. Squared minus 3 times 1 plus beta epsilon plus 2 plus epsilon is equal to 0. This thing is 1 plus 2 beta epsilon plus epsilon squared minus 3 times 1 plus beta epsilon plus 2 plus epsilon. Now I'm going to look at this, and I'm going to collect terms in powers of epsilon. So let me collect the things that have no epsilons in them. The order 1 terms they're called, right? So everything that doesn't have an epsilon is 1 minus 3 plus 2 and 0 on this side. I'm going to put a check mark here, right? This is a check that the base solution was correct. Oh, plus beta squared epsilon squared. Epsilon squared terms I'm not going to worry about, so that's why I didn't get it right. But thanks. Yeah, so there's that correction here. What if I look at the order epsilon terms? So this is everything that's multiplied by epsilon, right? Then I get 2 beta minus 3 beta plus minus, oh yeah, 2 beta minus 3 beta. Okay, where are the other epsilons?
There's one at the end.
Plus 1. Thank you. Right, and if you notice, this is exactly the same algebra we had before, right? Just a different way to do it. It's, I think, a more efficient way of doing it than this implicit differentiation thing. And this is typically how people work through linearizations of problems and higher order corrections. So as before. And if you're interested in higher order terms, you could work out higher order terms, starting with x as a function of epsilon is 1 plus beta epsilon plus gamma epsilon squared. And then you would also have to match terms of size epsilon squared to get the equation for gamma. So there's a thing, is there a problem here that collecting terms of order epsilon squared tells you that beta is 0? No, because you haven't worried about things with size epsilon squared. If then you put in this expression, you're going to be able to match those terms with the gamma. So this is something just like when you do repeated implicit differentiation, you get new information at every stage. The same thing here. You can work out the 1, and then you work out the beta, and then you work out the gamma, and so on, right? And I haven't shown it here, but all of those problems are linear. They're linear problems for beta and gamma at every stage. I seem to be having trouble getting through this material. So in fact, the crowning glory of this lecture was going to be an epsilon problem in a Sturm Liouville problem, which is showing something I really want to show. But I've only got 6 minutes left. I don't have time to do it. So I'm going to show you another easy example, and then I'll pick up the boundary value epsilon problem in the next lecture. Now there is one of the problems on your assignment that it's based on, so I apologize for the delay, but you still have until next Tuesday to do that, and hopefully you'll know how to start when you see the video of Thursday's lecture. For those of you that came late, remember from the announcement, I'm not able to be here to give a live lecture Thursday morning, so there'll be a video posted and accompanying notes sometime before Thursday's lecture. I'm hoping today, but it might be tomorrow. Okay, so let's look at it. Let's look at another example, which you've probably seen before, but I'm going to do the next correction, which you may not have seen before. So this is a time-dependent pendulum. Okay. Oh, right. I said right? So it's a rod on this thing that can spin around. And it's a rod, so you don't have to worry about like the string can go slack, right? Which makes another interesting problem. Okay, you're not going to like it, but I'm saving a little theta for later. So I've got a capital theta of t. This is an angle. So I'm going to talk about the scaled nonlinear pendulum problem. In 5 minutes. All right, so I'm going to have theta obeys a differential equation which is minus sine of theta. This is after scaling, right? There should be a length, there should be gravity, there should be a mass, but I don't have any of those things in this one. And I'm going to have theta at time 0 is going to be small, and its derivative is going to be 0, right? And something that you can show, this is like the a priori thing that we had before for the heat equation, the maximum principle. This is a priori result you can get even for the nonlinear pendulum that shows that theta of t is less than epsilon for all t. So if I start off with a small displacement, of course, it's going to have a small displacement for all time. I think this is physically reasonable, and you can show it mathematically. So let's look at what the dynamics look like when they're small, right? So I'm going to say, let's take this theta of t and say it's small. Right, so now this thing here has theta at time 0 is 1 and theta dot is 0, right? And I'm going to put in some higher order terms. Normally I would just put in 1, except I know that the next term is going to be 0. So I'm going to put in another term. So I'm going to take this and I'm going to put it in here. And of course, I should have put approximately, right? And I'm going to get a sequence of problems as I collect terms. So I'm going to have an epsilon theta double dot plus epsilon squared u double dot plus epsilon cubed v double dot is minus sine of epsilon theta plus epsilon squared u plus epsilon cubed v. And I'm going to use that sine of x is approximately equal to x minus x cubed over 6. Okay. Right, so then this is going to be minus epsilon theta plus epsilon squared u plus epsilon cubed v. I'm only going to keep terms up to order epsilon cubed. And so again, as an approximation, I'm only going to keep this. The only cubic term that lives is this epsilon cubed u, theta cubed over 6. And then I'm going to equate terms by powers of epsilon. Again, this is all equivalent to in a kind of implicit differentiation, but this, I think, is an easier way. So I get the theta double dot is minus theta. This is the usual linearized pendulum. Where you notice that the with the initial conditions, I get cosine of t. This has period 2 pi, independent, of epsilon. So the linear pendulum has this nice property that the periods don't depend on the amplitude, right? What if I look at order epsilon squared terms? Get u double dot is minus u. And I've got, well, I've already got the initial conditions I want, so I don't need to change them. And I shouldn't be moving at time 0, right? So I got those. And together, these tell me that u is identically 0. Remember, I said I knew that this term wouldn't give me anything interesting. Well, okay. So now you've seen it. What about the v term? So I'm going to get v double dot plus v is minus theta cubed over 6. This is minus cosine cubed t over 6. With v of 0 is 0, and the time derivative is 0. Okay, so, right, this is going to give you behavior that does depend on epsilon, obviously, right? And let me just say, okay, it's an exercise. I've shown you how to do this matching things term by term with a small parameter. And let me just say, this is an interesting problem. Have people seen this before? Okay, I'm hearing some no's, seeing some no's. Okay, okay, good. This is useful for you to see. This someone said this is perturbation theory. Yeah, perturbation theory, asymptotics. This is what I'm doing. It's a very useful technique in applied math. And for this problem, if you do some trig identities on cos cubed t, you'll find that there is a resonant term. There is a resonant term that leads to a period dependence on epsilon. So if you're interested, you can work through that. I was thinking of putting that on an assignment question, but that's pretty far from Math 400. So I'll just leave it at that. This is an example of how you do this game, and you'll see in the next lecture, which will be a video, at the beginning, you'll see how that is the same technique can be used in a boundary value problem. Now, what this is all about is, I guess, showcasing some of the power of the analytic techniques that we are using. Like when we look at this nonlinear pendulum, right, the solution to that comes with functions that aren't our friends necessarily, right? Yes, there is a solution. You can write it down. You know, you can invent a function that describes it. But it's only when you look at a small perturbation where you can make some progress with pencil and paper, and from that known solution, you can also look at some follow-up questions like, you know, if the amplitude is not that small, or you're really concerned with getting an accurate period time for small amplitudes, right? Then you can do some analytic techniques to get it. Okay, I'm on time officially, but 5 minutes late for my promise of 10:45, so I apologize. I'll end the lecture here, but I'll stay on for any follow-up questions that people have.